Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel. Today's topic of discussion is capacitor charging with initial conditions. Our objective is to examine the capacitor charging process when initiated from some prior charged state. This lecture operates under the presumption the viewer is intimately familiar with the capacitor charging process, as illustrated in the capacitor charging lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet or only dimly recall its contents, please take the time to do so now. You'll recall during the aforementioned lecture we examined three capacitor charging circuits, where the capacitor in question was assumed to start the charging process in an initially uncharged state. For all scenarios, VI, the initial voltage, was assumed to be 0 volts. Not so in this lecture. All we'll do is assume some initial voltage and see how this affects the electrical properties of the transient capacitor charging process. In an effort to save time and streamline this lecture, let's build off these previous examples. You'll recall example 1 was a series circuit consisting of a 12-volt source, a switch that closes at time t equals 0, a 200 ohm resistor, and a 15 microfarad capacitor. During the charging process, we learned at a time constant of 3 milliseconds. When VI, initial voltage of the capacitor, was assumed to be 0 volts, we observed the following properties. Current through the capacitor, IC of t, during the charging process was 60 milliamperes times e to the negative t over 3 milliseconds. Current through the capacitor experienced an initial surge of 60 milliamperes and decayed to 0 amps over 5 time constants or 15 milliseconds. Voltage across the capacitor, Vc of t, during the charging process was 12 volts times 1 minus e to the negative t over 3 milliseconds. Voltage across the capacitor started out at 0 volts, our initial voltage, and grew to 12 volts over 5 time constants or 15 milliseconds. Current through the resistor, IR1 of t, during the charging process also equaled 60 milliamperes times e to the negative t over 3 milliseconds. Current through the resistor and all elements in series with it experiences an initial surge of 60 milliamperes and decays to 0 over 15 milliseconds. Finally, voltage across the resistor, VR1 of t, during the charging process was 12 volts times e to the negative t over 3 milliseconds. Voltage across the resistor surged to 12 volts and decayed to 0 over 15 milliseconds. For the purposes of today's lecture, let's assume the capacitor initiates the charging process not at 0 volts, but rather with some starting voltage, VI, of 2 volts, oriented positive to negative top to bottom. Incorporating this initial voltage doesn't necessarily change the charging process all that much. Even the time constant remains the same at 3 milliseconds. After all, we're using the same 200 ohm resistor and the same 15 microfarad capacitor. Even the plots of electrical properties as a function of time don't change that much. As these plots illustrate, voltage across the charging capacitor still rises and still eventually reaches 12 volts after 5 time constants or 15 milliseconds. The only difference being that voltage does not rise from an initial value of 0 volts, but rather the initial value of 2 volts, meaning there is, at the onset of the charging process at t equals 0, a differential of 12 volts minus 2 volts, or only 10 volts across a 200 ohm resistor. Voltage across the capacitor as a function of time, Vc of t, can still be expressed as Vf plus Vi minus Vf times e to the negative t over tau, where Vi is the initial value of 2 volts, Vf is the final steady state value of 12 volts, and tau is the time constant of 3 milliseconds. Substituting these given values, Vc of t resolves itself into a simplified form as 12 volts minus 10 volts times e to the negative t over 3 milliseconds. This initial 10 volt differential is key to determine the magnitude of the initial current surge into the charging capacitor. With 10 volts across a 200 ohm resistor at t equals 0, an application of Ohm's law demonstrates the magnitude of the initial current surge will be 10 volts divided by 200 ohms, or 50 milliamperes. Note that this is less than the initial inrush of 60 milliamperes we earlier observed when the capacitor was initially uncharged at 0 volts. This reduction in inrush current should not come as a surprise. Less differential now exists across a path with identical resistance. As such, initial current surge decreases. Charge current, despite being of a smaller magnitude, however still exhibits similar behavior as previously. Notably, after the initial surge, it decays to 0 after 5 time constants, in this case 15 milliseconds. Current through the capacitor as a function of time, IC of t, can be expressed as 50 milliamperes times e to the negative t over 3 milliseconds. Because the resistor and capacitor are in series with one another, current through the resistor as a function of time is also equal to IC of t. As such, IR1 of t can also be expressed as 50 milliamperes times e to the negative t over 3 milliseconds. Voltage across the resistor as a function of time, VR1 of t, can be best expressed using Ohm's law, as VR1 of t equals IR1 of t times the constant resistor value R1. Substituting these given values, VR1 of t resolves itself into 10 volts times e to the negative t over 3 milliseconds. Again, R1 experiences an initial differential of 12 minus 2 volts, or 10 volts, then it decays to 0 volts by 15 milliseconds. Importantly, the summation of any instantaneous voltage drop across these two elements, the resistor and capacitor, must necessarily equal the voltage rise induced by the source. E equals VR1 plus Vc. The importance and utility of Kirchhoff's voltage law cannot be overstated. Too often, students lose their way in a confusing maelstrom of calculations when easier, more reliable methods lie well within their reach. For example, we knew voltage across the capacitor to be 5 volts. We by extension also know via the use of Kirchhoff's voltage law, employing simple addition and subtraction only, that the resistor must be dropping 12 minus 5 volts or the remaining 7 volts. With 7 volts across a 200 ohm resistor, a simple Ohm's law calculation demonstrates that 35 milliamperes must be flowing through it, and by extension, 35 milliamperes must also be flowing into the capacitor. In summary, if we know the instantaneous value of the voltage across the capacitor happens to be 5 volts, VR1 must be 7 volts, and both IR and IC equal 35 milliamperes. All 4 properties have been determined from a single data point using very simple skills. The more complicated question being, when does this event occur? Any and all of these same expressions can be used to solve for this desired time value given they occur simultaneously. Importantly, either expression should yield the same result. Let's use the expression for the voltage across the capacitor to solve for the time value that satisfies this condition. In this case, we know the instantaneous value of voltage across the capacitor to be 5 volts. 5 volts equals 12 volts minus 10 volts times e to the negative t over 3 milliseconds. What time value satisfies this condition? Subtract 12 volts from both sides. Divide both sides by negative 10. Take the natural log of both sides. Remove the negative signs on both sides of the equation and multiply both sides by the time constant. We're left with a time value of 1.1 milliseconds. If that seems too easy, we can always check our work using a more complicated method. What's the value of VR1 of t at the same 1.1 milliseconds? Substituting 1.1 milliseconds into our equation, we find that it's 7 volts, exactly as we predicted. Alright, let's move into another example, this time one building off what we learned in example 2 from the capacitor charging lecture. You'll recall example 2 was a series circuit consisting of a 24 volt source, a switch that closes at time t equals 0, 500 ohm resistor, and a 47 microfarad capacitor. During the charging process, we learned it at a relatively long time constant of 23.5 milliseconds. When VI, initial voltage of the capacitor, was assumed to be 0 volts, we observed the following properties. Current through the capacitor as a function of time, IC of t, during the charging process was 48 milliamperes times e to the negative t over 23.5 milliseconds. Current through the capacitor experienced an initial surge of 48 milliamperes and decayed to 0 over 5 time constants, or 117.5 milliseconds. Voltage across the capacitor, Vc of t, during the charging process was 24 volts times 1 minus e to the negative t over 23.5 milliseconds. Voltage across the capacitor started out our initial voltage of 0 volts and grew to 24 volts by 117.5 milliseconds. Current through the resistor as a function of time, IR1 of t, during the charging process also equaled 48 milliamperes times e to the negative t over 23.5 milliseconds. Current through the resistor, and all elements in series with it, experienced an initial surge of 48 milliamperes, which decays to 0 by 117.5 milliseconds. Finally, voltage across the resistor, VR1 of t, during the charging process was 24 volts times e to the negative t over 23.5 milliseconds. Voltage across the resistor surged 24 volts and decayed to 0 volts by 117.5 milliseconds. For the purposes of today's lecture, let's assume the capacitor initiates the charging process not at 0 volts, but rather with some start voltage VI of 6 volts, oriented positive to negative. Listen to me closely, not top to bottom, but rather bottom to top. If the goal of this charging circuit is to eventually charge this capacitor to 24 volts, positive to negative, top to bottom, let's simply assume top to bottom is the proper polarity. This initial 6 volt differential, bottom to top, can therefore most appropriately be considered an initial voltage of negative 6 volts. You'll note, despite the incorporation of an initial condition, the time constant for this circuit remains the same at 23.5 milliseconds. Let's make this an interactive exercise. See if you can derive the expressions for voltage across the capacitor as a function of time, Vc of t, current through the capacitor as a function of time, Ic of t, voltage across resistor 1 as a function of time, Vr1 of t, and current through resistor 1 as a function of time, Ir1 of t. It may be helpful to remind you that the general use function of voltage across the capacitor as a function of time is Vf plus Vi minus Vf times e to the negative t over tau. Pay attention to signs when incorporating this initial voltage of negative 6 volts. Also, it may help to remind you that the instantaneous differential at t equals 0 across the resistor determines the magnitude of the initial current surge. By all means, pause the lecture and try this on your own. If you're tracking, you should have arrived at the following values. Voltage across the capacitor as a function of time, Vc of t, can be expressed as Vf plus Vi minus Vf times e to the negative t over tau, where Vi is the initial voltage of negative 6 volts and Vf is the final steady state voltage of 24 volts. Substituting in these given values, Vc of t resolves itself into a simplified expression as 24 volts minus 30 volts times e to the negative t over 23.5 milliseconds. This initial 30 volt differential is key to determine the magnitude of the initial current surge into the charging capacitor. With 30 volts across the 500 ohm resistor at t equals 0, an application of Ohm's law demonstrates that the magnitude of the initial current surge will be 30 volts divided by 500 ohms, or 60 milliamperes. Recall that this is more than the initial inrush of 48 milliamperes we observed when the capacitor was initially uncharged at 0 volts. This increase in inrush current should not come as a surprise. With a negative initial charge, now more differential exists across the path with identical resistance. As such, current increases. Charge current, despite being of a larger magnitude, however still exhibits similar behavior as previously. Notably, after the initial surge, it decays to 0 after 5 time constants, in this case 117.5 milliseconds. Current through the capacitor as a function of time, Ic of t, can be expressed as 60 milliamperes times e to the negative t over 23.5 milliseconds. Because the resistor and capacitor are in series with one another, current through the resistor as a function of time is also equal to Ic of t. As such, IR1 of t can also be expressed as 60 milliamperes times e to the negative t over 23.5 milliseconds. Finally, voltage across the resistor as a function of time, VR1 of t, can be best expressed using Ohm's law, as VR1 of t equals IR1 of t times the constant resistor value R1. Substituting these given values, VR1 of t resolves itself into 30 volts times e to the negative t over 23.5 milliseconds. R1 again experiences an initial differential of 24 minus 6, or 30 volts, and then it decays to 0 volts by 117.5 milliseconds. Let's perform some instantaneous analysis on this circuit, incorporating an initial condition. Let's say we wish to know the instantaneous voltage across the capacitor, the instantaneous current through the capacitor, the instantaneous voltage across resistor 1, and the instantaneous current through resistor 1, all at time t equals 20 milliseconds, just shy of 1 time constant. Additionally, let's say we wish to know at what time value voltage across the capacitor crosses 0 and goes positive. Given this condition, what are the remaining properties? The instantaneous current through the capacitor, the instantaneous voltage across resistor 1, and the instantaneous current through resistor 1. By all means, pause the lecture and try this on your own. Here's a hint for the second set. 0 volts equals 24 volts minus 30 volts times e to the negative t over 23.5 milliseconds. What time value satisfies this condition? If you're tracking, you should have arrived at the following values. Let's start by substituting 20 milliseconds into the voltage across the capacitor expression Vc of t. This yields a value of roughly 11.2 volts. We could substitute t equals 20 milliseconds into the other time-varying expressions. However, we could also use much simpler, more reliable tools like series circuit properties, Kirchhoff's voltage law, and Ohm's law. Given an 11.2 volt differential across the capacitor, this means 24 minus 11.2, or the remaining 12.8 volts, must necessarily appear across the 500 ohm resistor. Quick application of Ohm's law demonstrates that with 12.8 volts across a 500 ohm resistor, approximately 25.6 milliamperes must be flowing through it, and by extension, 25.6 milliamperes must also be flowing into the capacitor because they are in series with one another. In summary, at t equals 20 milliseconds, Vc equals 11.2 volts, VR1 equals 12.8 volts, and both IR1 and Ic equal 25.6 milliamperes. For our second example, we know the instantaneous voltage across the capacitor Vc to be 0 volts. Therefore, 24 volts minus 0 volts, or the remaining 24 volts, must appear across the resistor 1. With 24 volts across a 500 ohm resistor, Ohm's law demonstrates that current through it, and by extension through the capacitor, must equal 24 volts divided by 500 ohms, or 48 milliamperes. In summary, Vc equals 0 volts, VR1 equals 24 volts, and both IR1 and Ic equal 48 milliamperes. Importantly, when does this event occur? We could use any of these expressions to solve for the time value that satisfies any of these conditions because they all happen simultaneously. Let's just use the expression for Vc of t. 0 volts equals 24 volts minus 30 volts times e to the negative t over 23.5 milliseconds. What time value satisfies this condition? Subtract 24 volts from both sides. Divide both sides by negative 30 volts. Take the natural log of both sides. Get rid of the negative signs on both sides and multiply both sides by the time constant. We're left with a time value of roughly 5.2 milliseconds. Moving on, consider this challenge scenario building upon the charging circuit we examined in example 3 during the capacitor charging lecture. You'll recall, example 3 was a series circuit consisting of an 8-volt source, a switch that closes at time t equals 0, a 250 ohm resistor, and a 2 microfarad capacitor. During the charging process, we learned at a relatively short time constant of 500 microseconds or 0.5 milliseconds. When VI initial voltage of this capacitor was assumed to be 0 volts, we observed the following properties. Current through the capacitor as a function of time, IC of t, during the charging process was 32 milliamperes times e to the negative t over 500 microseconds. Current through the capacitor experienced an initial surge of 32 milliamperes and decayed to 0 over 5 time constants or 2.5 milliseconds. Voltage across the capacitor, Vc of t during the charging process was 8 volts times 1 minus e to the negative t over 500 microseconds. Voltage across the capacitor started out at 0 volts and grew to 8 volts over 5 time constants or 2.5 milliseconds. Current through resistor 1 as a function of time, IR1 of t during the charging process, also equaled 32 milliamperes times e to the negative t over 500 microseconds. Current through resistor 1 and all elements in series with it experiences an initial surge of 32 milliamperes and decays to 0 over 5 time constants or 2.5 milliseconds. Finally, VR1 of t during the charging process was 8 volts times e to the negative t over 500 microseconds. Voltage across resistor 1 surged to 8 volts and decayed to 0 over 5 time constants or 2.5 milliseconds. You'll note voltage for the circuit never exceeded 8 volts. If left to its own devices, the final voltage for the circuit would always result in an 8-volt differential being applied across the fully charged capacitor after the passage of 5 time constants, in this case 2.5 milliseconds. For the purposes of today's lecture, let's assume the capacitor initiates the charging process not at 0 volts, but rather with some start voltage VI of 10 volts, oriented positive to negative, top to bottom. Yes, you heard me correctly, positive 10 volts. i.e. an initial value greater than what we'd ordinarily expect for a final value with this charging circuit. Yes, this is a little different from our previous examples, but it's well within your capacity to understand how the system works with a little thought and investigation. You'll note, despite the incorporation of an unexpected initial condition, the time constant for the circuit remains the same at 500 microseconds. Let's make this an interactive exercise. My first question to you is this. What happens during this quote-unquote charge phase when the switch closes at time t equals 0? Here's a hint. Consider instrumentation placed in the following fashion. Voltmeter C reads the voltage across the capacitor, positive to negative, top to bottom. Ammeter C reads the current through the capacitor, in to out, top to bottom. Voltmeter R1 reads the voltage across the resistor, positive to negative, left to right. Finally, ammeter R1 reads the current through the resistor, in to out, left to right. What happens when the switch closes at time t equals 0? Importantly, which direction does current flow through the system and with what polarity does voltage appear? Finally, is it really appropriate to call this a capacitor charging circuit? Here's a hint. The superposition theorem may help you out. By all means, pause the lecture and think about this. If you're tracking, you should have arrived at the following conclusions. Bottom line up front, this is not a capacitor charging circuit, but rather it's a capacitor discharging circuit. However, instead of completely discharging the capacitor to 0 volts, it only discharges it to 8 volts. If you want to think of it this way, this capacitor is initially overcharged to 10 volts, and this circuit will bring it back to 8 volts. As long as you keep track of signs, all of our previous analysis techniques hold true. Allow me to demonstrate. At t equals 0, one end of the 250 ohm resistor is at 8 volts, and the other end is at 10 volts. At t equals 0, this resistor therefore experiences a differential of 2 volts, only it's oriented positive to negative, right to left. Kirchhoff's voltage law supports this conclusion, where E equals VR1 plus Vc. Substituting in our given values, we find VR1 to be negative 2 volts. As a result, current will travel out of the capacitor, into the resistor right to left, and through the source top to bottom. Thus, current for both the resistor and capacitor will have an assumed negative direction. Ohm's law demonstrates with negative 2 volts across a 250 ohm resistor yields an initial current surge of negative 8 milliamperes, where the negative sign is indicative that current is traveling right to left. The superposition theorem supports this conclusion. At t equals 0, the 8-volt source and the 10-volt capacitor oppose one another. When these effects are superimposed upon one another, accounting for polarity, the resistor experiences a differential of 2 volts, positive to negative, right to left. the capacitor will discharge through the resistor and into the 8-volt source. Voltage across the capacitor as a function of time Vc of t can still be expressed as Vf plus Vi minus Vf times e to the negative t over tau, where Vi is the initial voltage of 10 volts and Vf is the final steady state value of 8 volts. Substituting these given values, Vc of t resolves itself into a simplified expression as 8 volts plus 2 volts times e to the negative t over 500 microseconds. Voltage starts out at 10 volts and eventually stabilizes at 8 volts over 5 time constants or 2.5 milliseconds. As long as you keep track of signs, this expression will work for any scenario. Current through the capacitor as a function of time, Ic of t can be expressed as negative 8 milliamperes times e to the negative t over 500 microseconds. Current experiences an initial surge of negative 8 milliamperes and decays to 0 by 2.5 milliseconds. Because the resistor and capacitor are in series with one another, current through resistor 1 as a function of time is equal to Ic of t. As such, IR1 of t can also be expressed as negative 8 milliamperes times e to the negative t over 500 microseconds. Finally, voltage across the resistor as a function of time VR1 of t can be best expressed using Ohm's law, as VR1 of t equals IR1 of t times the constant resistor value R1. Substituting in these given values, VR1 of t resolves itself into negative 2 volts times e to the negative t over 500 microseconds. R1 again experiences an initial differential of 8 volts minus 10 volts, or minus 2 volts, which then decays to 0 volts by 2.5 milliseconds. You'll note at 2.5 milliseconds, voltage on both sides of the resistor would be 8 volts, and the voltage differential across it is 8 volts minus 8 volts, or 0 volts, thus explaining the eventual halt of current, given the differential across it no longer exists. Is this an odd example? Yes it is. However, all of our previous analysis techniques remain valid and illustrated an important property of capacitors. Notably, capacitors resist sudden changes in voltage. In all of our examples, including those that had positive initial voltages, negative initial voltages, and even excess initial voltages, the voltage across the capacitor never underwent a disjointed instantaneous transition or a sudden reversal in polarity. That's the point. Capacitors resist sudden changes in voltage and are often employed in circuits that necessitate relatively steady or slowly changing voltage conditions. Also, it may be helpful to remind ourselves how the charge and discharge processes unfold. During a charging process, current rushes through a resistor and into a capacitor, while charging voltage across a capacitor rises. During a discharge process, current rushes out of the capacitor and through a resistor. While discharging, voltage across the capacitor drops. Any voltage experienced by a resistor is simply a consequence of the incoming and outgoing current experienced by the capacitor during the charge or discharge process. As a remaining exercise to the viewer, I invite you to solve for the instantaneous voltage across the capacitor, current through the capacitor, voltage across the resistor, and current through the resistor at time t equals 600 microseconds. Additionally, see if you can determine what time the capacitor reaches 9.5 volts. At this time, see if you can determine the instantaneous current through the capacitor, the voltage across the resistor, and the current through the resistor. By all means, pause the lecture and try this on your own. If you're tracking, you should have arrived at the following values. For our first illustrated example, substitute 600 microseconds into the voltage across the capacitor expression Vc of t. This yields a value of roughly 8.6 volts. We could substitute t equals 600 microseconds into the other expressions. However, we can also use much simpler and more reliable tools like series circuit properties, Kirchhoff's voltage law, and Ohm's law. Kirchhoff's voltage law demonstrates that with an 8.6 volt differential across the capacitor and an 8 volt differential across the source, the resistor will experience a negative 0.6 volt differential, where the negative sign indicates current will be traveling from the capacitor through the source. A quick application of Ohm's law demonstrates that with negative 0.6 volt differential across a 250 ohm resistor, approximately negative 2.4 milliamperes must be flowing through it, and by extension 2.4 milliamperes must also be flowing out of the capacitor because they are in series with one another. Again, the negative sign indicates that current is traveling from the capacitor through the resistor right to left and into the source. For our second example, we know that Vc equals 9.5 volts. Therefore, R1 must experience 8 minus 9.5, or negative 1.5 volts must appear across the resistor. With negative 1.5 volts across a 250 ohm resistor, current through it, and by extension through the capacitor, must equal negative 1.5 volts divided by 250 ohms, or negative 6 milliamperes. In summary, when Vc equals 9.5 volts, Vr must equal negative 1.5 volts both IR and IC will equal negative 6 milliamperes. Note all these events occur simultaneously. The remaining question being, at what time does this event occur? We could use any of these expressions to solve for the time value that satisfies any of these conditions because they all happen simultaneously. Let's make our job simple and just pick an easy one like VR1 of t. Ultimately, we're left with a time value of roughly 143.8 microseconds. Alright, that's about it for today. We'll examine capacitor partial charge and partial discharge scenarios in later lectures. In conclusion, we examined the capacitor charging process including initial conditions. We learned initial conditions merely change the starting point for voltage across the capacitor as a function of time. The resultant differential at the start of the process determines the initial magnitude of current. Regardless, the process unfolds within 5 time constants. Additionally, we kept our instantaneous analysis skills fresh with a couple illustrated example problems. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.